Here is an example on Bernoulli differential equation. In the last video we have shown how to reduce a Bernoulli differential equation to linear differential equation by means of substitution w equal y to the 1 minus n. So let's now apply this method to an example here, a specific example. So if we look at this equation here, dy dx plus 1 over x times y equal x times y to the power 2. Now as you can see here, n equal to 2, which is the power of y. So that means I'm going to use a substitution w equal y to the 1 minus n, so 1 minus 2, so that gives me y to the power minus 1. And let's call that equation 1 because we'll come back to it. Now, if we differentiate equation 1 with respect to x, so we will have dw by dx equal to minus y to the power minus 2 times dy dx using the chain rule. And now we're going to substitute this into, let's call that equation 0, into this equation here, and let's see how we reduce that to linear differential equation. So now let's if we solve for dy dx here, so I will have dy by dx equal to minus y squared times dw by dx, and now substitute in equation 0, and that will give us minus, let's just do that, minus y squared dw by dx plus 1 over x times y equal to x times y squared. Now note here we have a mixture of three variables. We got w, we got y, and we have x as well. So the idea is to eliminate y from this equation. However, it is not a good idea to try and rewrite every terms with y in terms of w using the substitution, because it becomes a bit lengthy. So what we're trying to do now is simplify that before we make the substitution w equal y to the power minus 1. So if we divide through, let's call that equation 2. If we divide through equation 2 by minus y squared, so we'll have dw by dx, so let me just write that, minus 1 over x times y over y squared, that gives me y to the power minus 1, so I'm going to replace that by w, and that is equal to minus x, because the y squared just cancels with the y squared there. And now this is linear first order differential equation, which we can solve by means of integrating factors. So now our integrating factor here, mu of x is equal e to the integral of minus 1 over x dx. So this is simply equal to e to the minus ln x, or just equal to 1 over x. You can check that. We now multiply our integrating factor 1 over x times by equation 3. So we will now have 1 over x dw dx minus 1 over x squared times w equal to minus x times 1 over x, which is just minus 1. Take another, running out space here. So now this equation, if you look at the left hand side, this is really, or simply just d by dx of w over x. So in a way what we are saying, if we differentiate that expression here with respect to x, we will get back to this one here. And the right hand side is unchanged. So now we integrate both sides. Again I will say 1 with respect to w over x. So my variable here is not just x, it's w over x, the whole thing, equal to the integral of minus 1 dx. So that gives me w over x on the left hand side equal to minus x plus a constant of integration. We can now write w in terms of x, which is minus x squared plus cx. So that is the general solution for our linear differential equations in terms of w. However, we are now seeking solution in terms of y. So we go back to equation 1, which is, let me just remind you of it, equation 1 where w equal y to the power minus 1. So we can now write that 1 over y for w equal minus x squared plus cx, or simply y equal 1 over minus x squared plus cx. And that is the general solution for w. Thank you.